Folks, welcome. I'm so glad that you're able to be here today for our AI Revolutions Symposium. I did want to start though, and recognize the tragedy that Nashville suffered yesterday. And I'd like for us to start with just a full moment remembering the lives lost, including Catherine Coombs, who was the head of the school, and was a graduate of Peabody College. So please join me a moment. Thank you. Our first speaker today is someone that I've had the pleasure of working with for the last several years, actually co-teaching with and doing research with, or at least working with your students, which has been a great pleasure. So Professor John Yang, Assistant Professor of Chemistry, has been doing some really outstanding work applying AI models. And it's nice to start with this because this shows us the full breadth of the applications of these models, which are not just large language models, but are also incredibly useful in other areas of science. So, John, if you'd like to kick us off with our AI Revolution Symposium. Thank you. And round of applause.
Thank you so much, Jesse, for the very nice introduction. You know, it's a great pleasure for me to speak today as the first speaker. I probably have to run right after for teaching. But the topic for today is about, through the looking glass. It sounds pretty bizarre, but probably it reminds you of, a fantasy or fiction story. It's, the Alice through the looking glass. That's basically, the season number 2 for Alice and Wonderland. Inside that looking glass, you're entering a special world. So a world where everything is a reflection, is reversed from the fact, from our world. If you want to stay in the same place, you have to keep running. So if you want to get something closer, you have to run away from it. So the entire thing is reversed. But one question I have for you is, why is that? You probably have your answer, right? A critical aspect I want to point out is how the mirror image could be different from its, original object. If you raise your right hand, if you raise your left hand, you can compare it. They look very similar. But if you are trying to superimpose them, I'm sure you're going to fail. The reason is because they are not the same. They are in reflection with each other. And that property is one of the most fundamental property in nature, which is called chirality. And that's exactly what I'm going to focus today. You probably think about, for this chirality, it's not only existing, for humans' hands, it's also part of the fundamental properties for molecules. And usually in as a chemist, we can label them as S configuration and R configuration. Still, the origin behind this phenomena is because every carbon has a tetrahedral structure. Van Hoff basically discovered that from about 150 years ago. The idea is when the carbon is, having 4 branches into the space in a tetrahedral mode, swapping 2 atoms will make them a reflection, and there is no way for you to superimpose them, just like the way you cannot superimpose, your left and right hand. Why does it matter? Well, for now, you probably think, am I entering another lecture of chemistry? It's just not probably, for AI. Wait for a second. So what I'm showing you right now is a drug molecule, especially on the left-hand side, of the slides. You're seeing a drug molecule, thalidomide. Thalidomide was approved as a drug by European, countries in 1950s. And that's the drug which was, designed to treat morning sickness for pregnant women. It should be good, but it turns out that for the two molecules you're looking at, they're not the same. They are mirror images to each other. There is a chirality on the carbon center, which I'm circling around here. So due to that chirality, because of the fact that, these two molecules cannot, superimpose, they're not the same thing. They actually have quite different properties. For the R configuration, the molecule you're looking at, as the first one, it can indeed help alleviate morning sickness from pregnant women. But for the second one, the S configuration, it can actually cause severe side effects. And the side effects is actually causing a lifelong disabilities, for the kids. It turns out that the misuse of thalidomide is the largest medical tragedy in the world, in the human history. It's causing 100,000 people, families, having the issue within 10 years before people discover that. And that's all about the seemingly similar to molecules, R versus S configuration. So that's the reason why what we are looking at here, chirality, is not just about some fundamental properties that only chemists care about. It's actually a matter of life and death. And one thing I want to mention is that the US, for some reason, was able to escape from that tragedy, largely because the FDA reviewer, Frances Kelsey, she fought against the big companies in Europe, basically had a strong opinion that we cannot approve the drug back to 1960s. And the only reason, the key reason behind that is because, she has a very strong sense of ethics and data ethics. The way how we collect them is extremely important, and also the safety behind biological data. So if you want to know more about that, I'm sure, Jesse's class is going to be the one to go. So how do we deal with chirality issue? It turns out that one of the most fundamental molecules in the world, enzyme, can be a very good treatment to the differentiation between mirror images. Those enzymes, you probably learned about that from high school, are biomolecules that can accelerate chemical reactions by 10 to the 16-fold. That's super fast. And they're also what we call stereoselective. Forgive me for the jargon. It's essentially about how you can differentiate the mirror images, how you can be, just making one thing faster, not necessarily is mirror image. And that's exactly the reason why I'm so excited about enzymes. Besides being able to differentiate molecules, there are so many impacts that enzymes can make. But natural enzyme, nature has evolved those molecules for a very long time. But if we are interested in any non-native applications, for example, if you are trying to, dissolve a drug molecule you just synthesized within the past 3 years, I'm sure there's no, spare part from nature that can help you deal with that, right? That's exactly the reason why we have to find a way. So when I started from Vanderbilt about 3 years ago, I told everyone that guess what? In the future, the way how future chemists deal with enzyme catalysis will be similar to the way how we deal with Amazon Alexa today. So if you want to get what you want, you just need to ask. That's exactly the reason why, we start designing a software ecosystem, computational ecosystem called Mutaxa. And Mutaxa means Alexa for mutant, because whenever you are trying to design enzyme, you have to do some mutation on it by replacing, some amino acids by others. So That's basically the idea. And behind Mutaxa, we have three components. One is the data, and the three components I have to tell you are deeply related to a data science institute. The first one is a database that integrates the enzyme structure, function, information. You know, we talked about chirality in the beginning, right? But there's no database that can tell you whether this enzyme is, you know, more towards S configuration or R configuration, one of whatever, left or right hand. And the second one is a software that enable high throughput simulation. Before the software, computational chemist has to do, you know, model one molecule at a time. But if you are trying to identify great candidates, you have to do like thousands of them at the same time, right? Our software, NZHTP, enables that. And the last one, the scoring function, is exactly where deep learning and machine learning can be extremely useful in, you know, making things happen. And we call them scoring function in chemistry community, because for anything, if you are trying to evaluate the performance, you just need to score the, you know, that's basically the idea. And I will also focus on the score function for the rest of my talk. So now I'm gonna read another story, and the turtle and the hare. How do we think about enzyme catalysis? Because, you know, I'm talking to a broader audience who are probably not so much don't care so much about the mechanism. So that's the reason why I'm using this example. The so-called selectivity, if you just want to get one of the mirror images, you are trying to make one of them a turtle and the other one is a hare. So you are trying to make one of the molecules win the race. And this race is a race of chemical reaction, you know. But enzyme is actually the race track. You have to design your race track so that, you know, one molecule can be faster than the other. When the two molecules get started, you know, they are like mirror images, they look very similar. But over time, once you have the enzyme in place, you know, one of them is going to be heading to the end point, end line, but the other one is probably still in the beginning stage or in the middle somewhere. In that way, you can separate them out. And just like, you know, one of them is a S configuration, the other one is R configuration, or we can just swap the order. It doesn't really matter. The key idea is that enzyme actually provide a racetrack to selectively favor one of the molecules over the other. And our job is to figure out which one does the enzyme favor and how do we engineer enzyme, you know, changing some amino acid to make the one molecule significantly favored by the over the other. And from chemical perspective, you know, the so-called read can be reflected from barrier. We know a lot of things take time, right? And this pretty much, we call them hurdle or barrier in life. And that's exactly what molecules have to go through. So for reactants to be transformed into product, they have to go, you know, overcome some hurdles. And that hurdle is what we call transition state. It's very hard to reach, and that's exactly causing some, you know, the reaction to be faster or slower. And basically, if you are trying to, you know, measure the rate, the critical parameter here is highlighted in kcat. So K is a rate constant, or called turnover. Don't have to remember so much things. Just keep in mind one thing. kcat is a way to know how fast the reaction can go. And the rate is extremely important. Remember from the previous slide, we are trying to make one of them a turtle and the other one a hare, right? So that you can differentiate them, which is essentially about how can you make the kcat different. And from this equation, you can also see kcat is related to another property, which is called delta G double dagger, the energy barrier. They're pretty much the same thing and can be converted from one equation. So I might use them interchangeably. And usually the higher the delta G, the lower the kcat. I'm going to repeat this component later when I'm getting to the point. But, you know, these are ways to represent how fast the reaction can go. So predicting the rate of enzymology is a holy grail challenge, and not definitely not one group in the world like my lab cares about. And so several groups have been using deep learning and machine learning protocols to predict, if I give you a, enzyme structure or sequence, how do you know the rate, whatever is KCAT or delta G double dagger? They propose the different protocols. They combine so many different informations, and some of them include the substrate information. The jargon comes again, smile string, but it's just a way of representing the molecule. You see thalidomide, right? There's a way of converting that structure into a one-dimensional sequence or two-dimensional representation, but essentially about representation. And there's a way of converting the enzyme, you look like the big structure, into a one-dimensional sequence. So they just put all those information into a deep learning model and, neural networks, and trying to predict, trying to build up a model for predicting, KCAT performance with given sequence and substrate information. But guess what's missing? Well, obviously they got a paper published into high-profile journals, right? But guess what's missing there? Chirality. That's exactly why I'm here, to talk about all the chirality, from the beginning. It turns out that if you just convert the structure into a one-dimensional sequence, there's no stereo information. There's no way, the three-dimensional architecture, and there's no way to reflect the difference. And I'm gonna, demonstrate this component later in some data, benchmark data. But the key idea for you, the conceptual component, is that chirality has never been incorporated in models like that before. And that's the reason why I told my students, see, we have to overcome this barrier again. But just to predict how the molecules with mirror image or mirror images with each other can be differentiated in the model. We curated the data set, since we are trying to design the model, we have to start from somewhere. And the place we started from is called hydrolysis. And that's also the reaction, the hydrolytic reaction, just decompose things, and you can differentiate the mirror, molecules with mirror image to each other. We curate data, the data set incorporates 204 hydrolyzed substrate complexes combined with, 408 negative samples. And all those enzymes are curated from the database, established from my lab. And for that distribution, you can see a wide distribution of delta G double dagger. I'm pretty sure most of you have forgot what delta G double dagger is, or you can surprise me by telling me what that is. Basically, delta G is the barrier. Remember, we talked about rate, right? The higher the barrier is, the slower the rate. So delta G, as you can see, range from like 5 kcal per mole to 23 kcal per mole. Simply tell us the rate distribution is wide and the barrier distribution is wide. We want to have diverse data, in our data set, simply because that's how we can train the model to be as generalizable as possible. Okay, so the next one, architecture of the model. We designed this deep learning model to consist of 2 basic modules. One of them is a classifier, the other one is a regressor. The classifier is taking, information like enzyme sequence, substrate information, and the critical component, the complex information, enzyme substrate, 3-dimensional structural complex as input, and trying to classify whether this complex structure is a reactive structure or not. Remember I talked about, the race track, right? Earlier, I'm saying enzyme is playing the role like a race track for 2 molecules to go. But there are so many tracks inside enzyme. The molecule might bind to the surface, might be binding to a random places. So we have to figure out what is the right binding site in the beginning. That's exactly why we need a classifier, for the first part. Once you make sure that this is the right binding site, you can go ahead and predict the value of delta G double dagger or the value of KCAT, just the rate of chemical reaction. For molecules that are in mirror image with each other, each one molecule, S configuration or R configuration can receive a number from this model, and that number is basically how fast they can go in the reaction. So the difference between the number basically tell you how good they are in chemical reactions, or whether we're able to separate them out in enzyme catalysis. The critical difference between my model and previous model is the incorporation of structural information, the enzyme substrate complex. And this is exactly where chirality can be learned. Well, up until now, you probably think, what do you mean by structure? Let me give you one example about what specifically got inside the model. Suppose we are talking about the fingers, inside the hand, If I'm talking, I can use distance map to represent my hand, such as each one of them is considered as a point and just measure the distance, in between like each of my fingers. So in that scenario, can you imagine the matrix form? It's pretty much symmetrical, right? There's no way you can differentiate them because everything just within that, and basically the information of chirality mirror image is never in there. However, if I introduce a reference, an external spatial point, and now besides just the fingers, I also incorporate that as a fixed point. Can I differentiate the two? The answer is yes, right? Because my hands are having different distance from the external reference point. Enzyme is exactly the reference point. So when you have enzyme inside, the symmetry between the images can be broken because enzyme is also chiral, it's also having mirror images. That's how you can break the symmetry. So that's exactly the component. That's where we can learn more about the chirality than what people have traditionally. We test the model in the training set and also test set. The Pearson and Spearman correlation, well, the values, it's really hard to comment on how the R is good or not. But basically, I can tell you based on the chemistry models that people can read the accuracy, this is definitely a very good performance. But to give you more rigorous definition of what do I mean by good, I have to perform benchmark against existing models. And the model we are having, NZ score, shows Pearson and Spearman correlation, the numbers you can read from the screen. And if we remove the complex information, which is the unique feature inside our model, right? If I remove that component, the performance drops significantly. But if we compare our model against the traditional model that people publish in Nature Catalysis, Dall-E, we still win, but just slightly, which also makes sense because their model has been trained over 20,000 data points. It might not necessarily the most accurate component that we can compare. That's the reason why I emphasize on the chirality or stereoselectivity comparison. That's the true test of how much the model is able to differentiate the mirror images. And two reactions that I won't go to the detail. I just want to let you know that we start from a mixture of mirror images. And after the reaction, basically one of them still remain, is not reacted. That's basically the hair, is not going to the endpoint within the time that turtle was able to make it. But the other one is basically the turtle, right? It can be reacted in a pretty fast fashion, and the second reaction is the same. And here is the data points we get. So to evaluate the reference, we are using sort of an e-value. Is simply a way to differentiate the two mirror images. experimental values are shown in black, and our model is shown in red, versus the gray model is the one people have published before. As you can see, in most scenarios, the model we propose, the NZ score, is, is much better in performance. Although there are several scenarios, we actually provide the opposite outcome. It's simply, the data set and many other components that can still be fixed. If you're interested, I can definitely talk more about the technical detail. So with that, I want to thank all my group members and funding agents. In particular, I want to thank Data Science Institute for giving me this opportunity and for the great collaborations I have with Jesse before and more in the future, I'm sure. And thank you all. I'm happy to answer any questions. Please.
So when you make this prediction for the KCAT, how do you actually verify this experimentally? Does it only apply to purified protein load? Constants are actually brought up in the product.
So for this KCAT, great question, actually. So sure. So the question is about what this KCAT predicted, refer to. Is it just refer to the, external, biological body, like in the cell, or is it referring to the, inside of organism? The previous model, like in the nature catalysis, is actually for the in vivo situation. It's basically inside E. coli. But our model doesn't care about whatever is in vivo or in vitro. It's just the KCAT value learned from the model system. Most of them are external scenarios. It's more like in vitro. And for the KCAT we predicted is basically a pair of, the structure of protein and also the substrate. And the substrate can be a non-native substrate. It's not just limited to whatever shows up in catalysis. And you also ask about how do we validate that? So many great questions out there. So to validate that's exactly why I have a wet lab. So the wet lab is there to validate the component. But let me tell you, it's extremely difficult. The reason is because for the database we curated is from external data where different labs might have different standard in terms of the measurement of KCAT. But the issue is when you have large amount of data, we always assume white noise in the data. Their Gaussian distribution. This might not be biased towards one direction over the other. So it's still about data sparsity issue. But
okay. One more question, either from online or
oh, actually, we have both like GN. The question is about the architecture of the data of the model, because when dealing with sequence data, and so just to make sure, when you're talking sequence data, what specific model you mentioned about? Right.